we're expecting Ross Mentemeyer from NC State to be presenting. Unfortunately, he had a personal emergency and is not able to be with us today. And luckily, Brian Blanton, who is the Director of Environmental Initiatives at RENC, was kind enough to stand in and is going to be presenting some work that's somewhat similar to Russ's. So thank you, Brian, and thank you, everyone, for tuning in. The title of the talk today will be Simulating Storm Surge for Coastal Hazards and Risk Assessment. As I said before, it'll be presented by Brian Blanton. He is RENC's Director of Environmental Initiatives and a coastal oceanographer with more than 15 years of experience in coastal hazards and risk assessment, high-performance computing, and earth sciences data analysis. As I said, he leads the Environmental Sciences Group here at RENC with Ray Idazic, and that group builds connections between water-themed sciences and applications through sustainable software development and data management practices. His research usually involves applications of storm surge and the wind-wave model ADCIRC for problems such as how FEMA computes coastal floodplain statistics, rapid statistical forecasting of storm surge, and risk-based coastal evacuation routing. Brian is hang on here because we're winging it a little bit. He's holds a PhD in marine sciences from the University of North Carolina at Chapel Hill, and also BS in mathematics from Armstrong State College, which is in Savannah, Georgia. So enough from me. Welcome to Brian, and enjoy the show.
Great. Thanks, Karen, for that introduction, and hello, everyone. I see some names rolling by on the attendees list that I recognize, which is good. This is not a venue I'm typically speak in or give presentations in, even though at RENC we certainly think a lot about, big data, data sciences, and the like. So this does fit into the general data sciences realm, although it's not going to be specifically about data science per se. It's really an application of some models that exist and that have. I'll talk a little bit more about that as we go forward. And this is really kind of an eye candy show. A lot of figures. There's only one equation, and it's not even really an equation. It's more of a proportionality. So it'll be kind of lightweight in that regard, and just show you some figures about how we go about computing a fairly large statistical problem that has a lot of important and practical implications that we'll talk about. So this is the opening slide. You see a picture of sort of a satellite picture of a very large hurricane. So hurricanes drive a lot of the work we do at RENC, at least within the environmental sciences and earth sciences group, and a lot of connectivities to other parts of there we go, to the environment, and also other parts of the research community as well as federal agencies. So, so the grounding, I want to say a little bit about what we're doing and why we're doing it in the next couple of slides. But we're going to talk about hurricanes at a very large scale, high level, I should say, storm surge, which we're going to define. Sort of the goal here is to really talk about how at least one part of the community thinks about the risk of living at the coast, which has got, some complications, due to things like climate change and sea level rise issues, whether or not any particular community or state or region thinks those are real problems. They're real problems. They are having an impact today, and they'll continue to have an impact far into the future. So this is more of a physics talk and a lightweight physics talk than a big data talk, as I mentioned earlier. The files that we produce are large, and there are a lot of them, but it's not really a big data problem. The data is highly structured and organized. This is not something that applying machine learning or language processing is really going to help us understand the data better. We understand the data, the question is, what do we do with the data to turn it into products that can help the whole discussion about risk and living at the coast, and basically how does the Federal Emergency Management Agency go about trying to hedge the risk or hedge the bets on really large disasters and catastrophes that have a huge financial cost to them. So this has a couple of pictures. The long one in the lower left is the Port of Savannah with a pretty big boat going up it. The one on the lower right is the overtopping of a flood wall during Hurricane Katrina, somewhere along the Mississippi or Louisiana coast. I can't recall. So these kind of problems are real, and they're having a huge impact, certainly in the last couple of years, with storms like Hurricane Sandy, and even a little further back into the mid-2000s with Hurricane Katrina and Rita. So very briefly, I've got a lot of interest, unfortunately. Largely R&D plus application somewhere in the coastal oceanography realm. Me and others that I interact with quite a bit are really interested in the way tides propagate through relatively small areas, because tides are really important to the way that the coast, not only coast forms, but also to the way, for instance, fish species get from offshore where they're born or spawned as larvae, all the way into the coastal behind the barrier islands environments where they actually have to sort of grow up. So tides are a really important part of that, and we understand the physics fairly well. There are a lot of sort of regional and local issues with the tides that are still being studied. I'm not going to go through this in a lot of detail, but if you look around, the probabilistic applications flood insurance studies for FEMA is where this talk is really going to be based. And we'll come back to some of these very, very briefly later on. So probabilistic wind, wave, and surge studies. This is largely about the way FEMA computes or derives the flood insurance rate maps that are used to define hazard zones for which property insurance rates are set if you're in a flood zone. And so the question that is, the general high-level question is, where are the 100 and 500-year limits of inundation? In other words, given a 100-year storm, however you choose to characterize that, where is the water going to go? Because if you're on one side of that line, you pay insurance. If you're on the other side of that line, you may opt not to buy insurance. This is kind of generally where we are. There's a real big demand for high-resolution studies because very small features require relatively high resolution in order to simulate accurately, and they can, in some cases, have very strong constraints on the surge propagation, the way the water gets to the coast. A lot of the research into these methods are post-Katrina. Katrina rung the bell. I'll have a little bit more to say about that. And I should say I'm going to skip a couple slides as we go along because sometimes it's not entirely clear. I put this together pretty quickly, so I wasn't really sure where I was going to go with some of these. But but if you think about the way information or processes are laid out in terms of how big they are, big in space and big in time, we're sort of in the 1 day to 1 week time scale with storm surge. I mean, hurricanes, generally are about a week long. Their impact on the coast is the actual landfalling event is actually on the order of a day. Now, the impacts can be quite long-lasting, but the actual physical event is somewhere in sort of the 1 to 10 week, 1 day to 1 week time scale. Spatial scales, essentially from 100 meters to 100 kilometers. 100 kilometers is, about a degree. So, that's a fairly decent scale. And in terms of the whole spectrum of possibilities, though, climate change is a process or a sequence of unfolding events that's got a very long time scale and a very large spatial scale. And then if you go all the way down into the lower left corner, we're talking about molecular processes, the processes of diffusion and things like that, actually turbulence in the water, for example, going all the way to heat. That's an extremely small scale feature. we're right in the middle of this sort of this spectrum of things. And so models which are really good in this middle zone that we'll be talking about, meaning for coastal dynamics, don't work at all really at either one of the other ends of these scales. So where we're talking about processes that are sort of in our daily life time scale and spatial scale. So I'm going to talk a little bit about why study storm surge, a little bit about FEMA, how we compute it, and then what we actually do with some of those results. And certainly, to be fair and honest, you know, the Renaissance Computing Institute is involved with this, but so is the UNC's Institute of Marine Sciences, as well as the Coastal Resilience Center at UNC, which is a Department of Homeland Security Center of Excellence that's kind of in its second phase here. We had a first phase of that through something called the Hazard Center, and that was actually quite effective in a lot of different ways. One of which was promoting awareness of things like the model that we'll talk about as we get slightly or further down. Certainly, the Corps of Engineers is a big player in this whole area, as well as NOAA, and there's a lot of private sector work, particularly from insurance firms, as well as consulting firms, which actually carry out a lot of the studies that FEMA needs to conduct. So why study storm surge? Well, very quickly, 44% of the world's population lives within 150 kilometers of the coast, and that's getting larger. So what's going to happen is that as sea level rises, that population initially is going to get compressed into a thinner zone. And we're talking about over a scale of 30, 50, 100 years, not 5 to 10 years. And now it remains to be seen whether or not the population will as it gets compressed, actually start to move upland. But ultimately, there's not going to be much of a choice. But that's really the issue confronting, I think, the coastal zone on the scale of 100 years. So there's a lot of sort of policy implications for some of the stuff that projects we work on. For instance, what if Hurricane Katrina had been a Category 5 storm? It's not out of the realm of possibility. The same thing is true for Hurricane Floyd, which was 1999 and impacted a lot of North Carolina and a little bit of South Carolina. Had those been Category 5 storms, we would probably be having a different level of discussion today, but also those areas would be very different than they are 10 years after those events have occurred. But the question is, well, what if? Because we do need to think about these what ifs over the very long term. So FEMA's coastal flood zones are the instruments that are used to set insurance rates on the coast. And if you have a federally backed mortgage and you live within one of these zones, you are supposed to carry flood insurance. So this is really we want to understand storm surge. We understand the physics very well. What we need to know is how do we compute things at ever higher resolution to be more accurate in the way some of these zones get delineated. Because again, the small scale features like levees or roadways can have a very big impact on the local details of what these maps actually need to look like. And we're actually not really there to the point where these maps from the new way of computing things are really effective yet. They're still being drawn, and in many cases they're being discussed at the community and government level and still being vetted. So we're not really to the point where we can show those kind of maps because frankly we don't have them. So sea level rise, climate change impacts on the coastal zone in general. The big worry now in terms of uncertainty is what happens when ice sheets really start to melt. That is the big level of uncertainty sort of in the next, at least in terms of research, in the next 5 to 10 years that the climate community is trying to get a handle on, because that could be sort of the order one problem in the long term. Barrier islands get breached by hurricanes and the storm surges and the wave impacts that go with the high winds and something like a hurricane. This is a stretch of North Carolina's coast before and after Hurricane Isabel. Isabel made landfall somewhere in late September of 2003, which is the lower picture, and you can see that several fairly large holes were punched through this relatively thin part of the island or the Outer Banks rather, and destroyed the only roadway in and out of this entire area. So what happens in these cases is that there's enough need for that one specific road that the Corps of Engineers comes in and puts the sand back and the roads get rebuilt. And over a very long term, that's probably not a sustainable way of going about life in this area. So, you know, at some level, these kind of issues as we go forward in time are going to have to be addressed in a different way. We can't just continue to repair and rebuild and renourish beaches forever. So it will require ultimately a different way of thinking about some of these problems. This is Ocean City, Maryland, before Storm Sandy, and you'll see a lot of cars near the beach, a lot of people on the beach in a very long pier going out into the water, and this is afterward. You know, kind of understandably, everything's been sort of wiped out, and you know, this area is going through a lot of the discussions that other communities are going through about what do we do how do we go into the future, given all the uncertainties with things like storm surge and climate and storm frequencies. So anyway, this is just a little bit about sort of the impact level thinking about why some of this is important. But the bottom line ultimately is that if you pay flood insurance, how do those rates actually get computed, or at least the zones delineated on a map? And so on the right-hand side is a picture of a flood insurance rate map, an old one, for a part of Bald Head Island in North Carolina, which is a very high-rent district or area. The white that you see is sand, not only from the beach but from golf courses. This is a really there's a lot of wealth in this area, so obviously protecting that is fairly important. There are lines on this map which may be hard to see, and if a property is between one of those lines and the ocean, you're essentially in one of these 100-year floodplains. And so these kind of maps are used to identify whether or not a specific property needs to carry flood insurance. So these maps are the official map of a community where FEMA has delineated these special hazard areas and then basically assigned some sort of risk level so that insurance rates can be set in a somewhat rational way. There's a lot of criticism about the way the rates themselves are set, and a lot of discussion about how that can be overhauled to make the whole situation a little more fiscally sound, and I'll show you a picture of why that is in just a second. FEMA administers the flood insurance program, and their overall mission is that, to reduce the loss of life and property, which is, something that they're actually, in my opinion, quite good at. It's an extremely hard problem because the loss in this case is not just due to hurricanes, it's due to just about anything. And so they became part of the Department of Homeland Security in March of 2003, and they're sort of, at least in the coastal context, they publish and defend the flood insurance rate maps that we're talking about. And this presentation will be available through the normal NCDS DataBytes mechanism, so I'm going to gloss over some of it. But here's the financial problem. This is a chart of the essentially premiums and claims at FEMA over the last 40-something years. And for quite a while, the green line I highlighted, and this is the premiums minus the claims. So it's sort of the annual or the aggregated net, if you will. So as you go along, there's been periods where up to about the mid-1990s where things were largely in balance, and that's there's a number of reasons for that. One, there may not have been particularly large disasters overall. Two, the types of properties or people that needed insurance may actually that population may have been actually quite different. As you go along, though, you can see that the green line, the premiums are sort of getting larger than the claims, which is good. The total operating result, however, has essentially always been negative, at least in the last 30 years. The big dip in 2005 is Katrina and to some extent Rita rolling into the Gulf of Mexico and impacting the northern Gulf. So what happened is a whole bunch of claims came in 2005 that had to get paid out in 2006, and FEMA had to borrow in order to recover that, or in order to make those claims or pay those claims, and it hasn't recovered. And it's and there's probably a lot of analysis as to how that can be fixed over the long term. I'm not an expert in that, but this is something that really struck me as interesting, because if this type of event starts to occur more frequently, then this kind of situation only gets worse. So this is, not really a sustainable operation from a business standpoint. So FEMA instituted the national, the flood map modernization program to basically update all the coastal maps on the East and Gulf Coast, and actually probably into the Gulf of, the Great Lakes area as well. Many of the coastal firms, the maps themselves, were significantly out of date, either in terms of not representing very short-term development, which has a big impact on the floodplain, but also just the fact that many of them, the data that went into generating those maps was in some cases 20 or 30 years old. So the maps ultimately should keep pace with not only development, but also our changing understanding of the environment, whether or not that's from the way hurricanes get characterized or the technology that's used to compute something like storm surge. So this has been a big effort. It's taken many millions of dollars to get to where we are right now, and the North Carolina component to this is what we're going to talk about next. So the actual storm surge component is computed literally with computer models, and we need, I'm going to skip this slide because it's a little wordy, but here's the basic process. We start with some storm surge and wave modeling activities so that we can understand the statistics that go into something like defining what is the 100-year flood. And the 100-year flood, by the way, is a really bad way of thinking about it. And I thought I had a slide about this, but maybe I took it out. The right way to think about a 100-year flood is that it has a 1% chance of occurring in any given year. And so, the general misnomer or misconception is that if it's a 100-year event, well, then it should only occur nominally once every 100 years. But that's completely untrue. And 2005 is the classic example of why that's not true. You had several relatively close to 100-year storms rolling into the Gulf of Mexico, and clearly that was over a time span that was definitely shorter than 100 years. So when you think about it in terms of annual chances of occurrence, then what you realize is that, well, that's 1% occurrence interval can happen in any given year. And admittedly, it's unlucky if it happens 5 years in a row, but that doesn't change the facts that the statistics, are what bears out whether or not an event falls into a category of, is it a 1% or if it's a 2% annual event, that relates to the 50-year period, or 50-year occurrence interval. So we compute a bunch of statistics. There's then some subsequent analysis that accounts for more details about the way that the beach is shaped, for example, and the way waves run up onto that beach. And then that data goes into the map drawing activity. So our work is entirely on that very first square of storm surge and wave modeling statistics. The other parts are complicated, and those are done largely by consulting firms who have the techniques in-house to be able to do the map drawing, for example. So that's all we'll really say. I'm going to skip this one. Here's the kind of the most important part. Somehow we have to represent the history of hurricanes in a probabilistic way. So this is done typically through something called the joint probability method, where you look at all the parameters of the hurricanes in a certain area and you develop distributions for those, and then you can sample those distributions and essentially create a population of synthetic storms that represent the climatology of the hurricane. So on the left-hand side is all the hurricanes since 1890 something. And in the North Carolina area, there's actually about 14 or so hurricanes that have impacted North Carolina over the last, let's say, 50 years. So we have 14 data points with which to try to characterize the the 1% flood level. So that's actually an extremely data poor problem. I mean, we actually need to have more data to do that, and really the only way to do it is to do something like joint probabilities. So we take those 14 storms, develop the distributions, and then we turn them into, look at the bottom row here, it says FEMA Region 4, North Carolina. So we've taken 14 storms and we've basically bootstrapped our way through joint probability into a very dense representation of the hurricane climate. And there are 700 or so storms that we've derived out of that population of 14. There's a slight amount of art to that, there's no doubt about it, but this is really the only way to get at how you can fill in the data gaps, if you will, when you've only got 14 storms over 50 years. And you really want to get out to about the 100-year time frame or longer. I was going to skip this, but maybe I won't. So let me just say, what is storm surge? Well, storm surge is what is the result of wind basically pushing water toward the coast. But it's not really the wind that's causing the storm surge. It's the fact that you've got this water that's being pushed by the wind that actually hits up against a boundary, the coast, and it's got nowhere to go but up. So that's what storm surge is. So this is a sort of a picture or a cross-section of a hurricane, and you can see on the right-hand side that there's some part of it says wind-driven surge, and that's just kind of the water as it gets close to shore piling up. There's other components to the storm surge that are important, but not at the level of this discussion. But again, this is available for people that want to know a little more. I'm going to skip this because it's too hard to think about. So why use computer models? Well, I mean, fundamentally, the problem is that the problem is complex. I mean, we can't represent hurricanes completely analytically. We can't write down a description of all the parts of a hurricane that are important. We have to use parameters to do a lot of that. And the wind fields in a real hurricane, this is a picture from Hurricane Hannah, courtesy of Gary Lackman at State. And you can see all this little variability in things like the wind speeds, all the wiggling and stuff. Now, that wiggling doesn't necessarily matter so much to storm surge, but it's an important to realize that there are other variabilities that we have to use computer models to get at because we can't just write down expressions for this. The geometries of coastal regions are very complex. There's nothing simple about them, so you can't get away with saying something like, well, there's a nice straight coastline and the depth in the continental shelf waters is extremely flat. I mean, you can't say that. So then there's not enough observations to be able to deduce extreme events like hurricanes. To get a 100-year resolution, you would really need a lot longer time series in order to do that. But the other thing is that time series are only available of something like water level, for example, are only available at a handful of locations in any given state. So in order to fill in the gaps, we just have to use computer models. So the way that we do that, typically, this is in general, this is not just for our problem. You start with Newton's laws if it's a sort of let's say, a fluid problem or a physics problem, and you turn it into partial differential equations that represent the problem you're interested in. Then you go down diagonally to the left and you turn it into an algebraic problem that the computer can actually solve. And then you turn that algebraic problem into software, and that software part is the AdSurf model. It's doing that last piece from AX equal B and then running it on a supercomputer if it's a very large problem. So AdSurf was developed at UNC and Notre Dame. There's a fairly small, tight-knit community of experts that are continually contributing to the code and maintaining it in a sort of very rigorous software way. A little bit of a detail, it's formulated with triangles instead of squares, and that's a really important feature because with triangles you can sort of very easily map your way into very high resolution. And the picture on the right is an AdSurf grid. And it's maybe a little bit hard to see, but in the very deep ocean, that's actually Bermuda out there on the, right there. And there's, the triangles out here are pretty big because the water's deep and we don't need the resolution. But in North Carolina, we actually do need the resolution because that's where the problem is really important to us in this particular case. So you can't even see the triangles there, it's so dense. And so now we're going to zoom in just a little bit. Actually, I'm going to come back to that. So here's what the grids actually look like. So in the lower Neuse River, which is in part of Pamlico Sound in North Carolina, again, the red is the triangle network for the model. And you can see that the triangles get pretty small as you go up into these rivers, because as the rivers get narrower, typically, the flow speeds get higher, so you need a little bit better resolution in order to resolve the physics. Here's another look at that. This is the Barrier Island system along North Carolina. When I showed you the Isabel breaching situation early on, that was actually right here. So this is our way of essentially representing that part of the coast. This is an inlet. This is where the water is coming from the deep ocean and sloshing into Pamlico Sound primarily through the interaction of tides going back and forth through this inlet. This, the high red here is high elevation. So these are dune lines. And dune lines are really important because they actually provide the first real level of protection between the open water and then a bunch of development that's typically behind the dunes. So when you lose the dunes, you lose that first level of protection. So that's something that communities in general are grappling with all the time, is how to preserve and protect the dunes, but also really kind of fundamentally balance between the protection level that it provides and something like economic or property development. I mean, that contention is really is a very hard problem, to say the least. So these are very large problems. And let me just skip ahead here. We typically run this on several hundred to several thousand CPUs on a big computer. We take the grid, that in this case, this is North Carolina. The little patches of color are the way we subdivide the AdCert grid and shove each of those onto a core on a big machine. And so this is just the consequence of the resolution. If we want very high resolution representations of, not only the coastal area, but also the response in terms of storm surge, we have to bite the bullet. We have to resolve the problem appropriately, and then we have to have the computer resources to be able to actually run these simulations. I'm going to skip, sorry. So I want to go back to the JPM model here, the joint probability model. I said a little bit earlier, it's a little hard to see, but these are the 14 or so tracks that have intersected this box, which had some impact on North Carolina. And then through the magic and art of joint probability method, you can take that and you can generate this set of tracks, which statistically represents and fills in the data, the parameter space that are sort of encompassed by, that encompass these observed tracks. So for each of these individual hurricanes, or representation of a hurricane, we compute a storm surge solution. So we take that track and we shove it into the AdCert model. The AdCert model knows what to do with it. And here's the storm surge that results from just two of those tracks out of the 675 in this case. Here's the track. The hurricane went basically like this. This was a fairly strong storm. The redder the color, the higher the water, and this is in meters. So this is 4 meters, which is 13 feet of water. And as you can see, this is Pamlico Sound right here. This is essentially a sheltered area because the barrier islands protect it largely from communication with the open ocean. So there's not a lot of water that ever really reaches from the open ocean into Pamlico Sound. But if you look at this, you can see a lot of very high water in very shallow areas in Pamlico Sound. Well, the only place it can come from is within the sound. Think of it as a bathtub. So if you blew water on a bathtub, then one side of the water is going to go up, the other side has to go down. And that's exactly what you're seeing right here, is that the water that's flooding this area due to this particular hurricane wind and track is coming at the expense of the other side of the sound. It's not coming from the open ocean. So here's another track. This is actually even stronger. And it sort of comes in. This is essentially where Wrightsville Beach is, if you know where that is. In general, in a hurricane, the winds are strongest in the right front quadrant. And in this case, here's the storm surge response. Now, this is 7 meters as opposed to 4, so this is a much more intense storm that has larger storm surge. So these are sort of two examples of what these kind of simulations look like. Each of these simulations produces quite a large amount of output, so it's big in that sense, but again, it's very organized. We know exactly what the structure is. So it doesn't, to me, fit into the typical big data realm, although some people argue that it does. So then so let me go back one step. So everywhere you see color, there's an AdCirc node. There's a place at which the computation is happening. So now we have to turn this sequence of 700 or 675 storms into a probability surface. And so I'm going to show you what that looks like at one node. So in the upper right, forget the text on the left. It doesn't particularly matter. So you can see here the blue dots represent a storm surge for every single 675 storms at one specific location. So you can see there's a lot of scatter, but if you just rank order them from smallest to largest and you accumulate that, then what you get is essentially a cumulative distribution function. And then you can go into that cumulative distribution function and say, where is the 0.99 value in a cumulative distribution function tells you what the storm surge is that would be equaled or exceeded only 1% of the time. Now that requires a little bit of thought if you're not used to thinking about return periods and frequencies, but the bottom line is that the higher out you go out on this cumulative distribution function, the higher the storm surge and also the more rare or infrequent it is. So then we can take that cumulative distribution function and we can go in and sample it at very specific frequencies and say, well, here is the 1% or the 100-year, in quotes, value at that location for storm surge. And it turns out it's 3 meters or roughly, 9.5 or so feet. So we do that at every single node, and we get this. And this is a little bit of a zoom in here. This is now just taking that 1% value at every node and coloring it. Whoops, sorry, let me go back. There we are. So what you can see in the open coast, this is Wrightsville Beach area. Wilmington, North Carolina is right here. This is the Cape Fear River. The map I showed you earlier of Bald Head Island, that's Bald Head Island, just for some reference. So this is, now these units are in feet. FEMA requires feet. It just is, although it drives me up the wall. So here's the 1% or the 100-year value. Nominally, this is 12 feet along here, which means that in any given year, given a hurricane event that's going to come close to this area and make landfall in this area, there's a 1% chance that the water level will be 12 feet or higher. That's the way to read these. So we've done that for the entire coast of North Carolina, and there's a lot of, obviously, I'm telling you how this works in 30 minutes, but this took about 2.5 years to get through. Not because we didn't know how to compute it, it's that there's a lot of sort of hidden problems and pitfalls and, frankly, anxieties about how you go about computing this at high resolution on such a large scale. Not only that, these are dynamic models. They're solving equations of motion, so they have essentially stability constraints that have to be met. The way that you design the grid, the underlying triangles to represent the topography is extremely important, and the solutions can be very sensitive to that. So all of that took quite a while to grind through. So let me go back now to this. We've computed some flood statistics. FEMA and other contractors, certified mapping firms, take that data and they basically project that data up way on the land and account for things like buildings and property details that we don't resolve in a model like AdCirc. And then the maps get produced, and we're in the process in North Carolina and also in the FEMA Region 3 and FEMA Region 2, which is in the New York area, of having those maps created from new statistics to update all of the maps along that part of the coast. Those updates are being drawn and discussed at an internal level right now. And by the way, we, RENC or UNC, we don't see those updates. That's downstream from us, and that kind of information doesn't get out into the community until there's been a whole lot of scrutiny on it, and that's kind of where we are in this whole process. So back to this. So I've really characterized this first box in a nutshell. Let me now say, so that's the end of what I had to say about floodplains. That's how the process sort of generally works. What I haven't talked about, because A, it's not my area of expertise, and B, well, I mean, that's the fundamental reason, I guess, is that it's hard enough to compute the statistics. But I don't want to leave it off with just saying, well, that's kind of what we did. So this model AdCert gets used for a lot of different things, and I want to show you just a couple of things about where we're going in general, because this floodplain problem for us that I've just described is essentially, I mean, it's done. I mean, our part, we hope, is done. And I don't anticipate being involved in another one of these ever again. It's anything that's got regulatory implications has a concomitant amount of stress to it that is actually sometimes very hard to, well, it's hard to deal with. So other things we're doing. So you have all this dynamic model, AdCert. It turns out it can be very expensive to run. If you wanted to compute a forecast for a storm that's actually coming ashore, if it takes 6 or 8 or 10 hours for AdCert to run, well, the emergency managers need that information much faster than that. And we've gotten that time down to nominally 2.5 to 3 hours. And it depends a little bit on the grid and how resolved things are, but that's nominally where we are. But you can take all of the data from those 700 storms, and you can turn it into what's called a response surface. And then you can very rapidly evaluate a statistical forecast based on all those dynamic forecasts in a matter of seconds as opposed to hours and hours. So here on the right-hand side, let's just pick that first. This is the actual dynamic AdCert, full-blown AdCert solution for Hurricane Isabel. And Isabel came ashore right here. This area, are we on time? Are we okay? 2 minutes, 2 or 3 minutes? Okay. This is the area that had the breaching of the islands that I showed earlier, and this is the storm that actually caused it. So you can see that there's a lot of high water in Pamlico Sound up in these rivers. And here's the surrogate solution, surrogate meaning statistical. So we take all the data that goes into the floodplain calculation, we do some statistics on it, and then we can very rapidly compute, given exactly the same hurricane track, what would have been the prediction from a statistical standpoint for something like Isabel. And if at a very high level, these are qualitatively very, very good. There's some details that are missed, but you can't get something for nothing, as it were. And so there's some level of acceptance. If you want rapid and fast and early information, you're not going to get it at the same level of fidelity that you would if you had many, many hours to wait for a solution that's fully dynamic, highly resolved. So we're taking the high resolution data that we've already computed and basically statistically using that to develop statistical models. We're also looking, and it amounts to a very large least squares problem. You can't see me, but I've got my little fingers in quotes because other people in the community are thinking about how neural networks work in this case, and we're sort of looking at some of that ourselves. That's another interesting way of looking at some of this. Another thing, so if you're talking about forecasting, if you have just one realization of storm surge from a model, you don't really have a way of assessing how uncertain, or how certain rather, you are about that particular outcome of that experiment. What you really need to do is run dozens to hundreds of simulations on the left-hand side, this is a sort of a fictitious hurricane track where it's actually been sort of smeared left and right based on the true statistics of the way hurricanes evolve. And this is 81 in this case hurricanes that can be then used to essentially drive that fast statistical model to very rapidly come up with exceedance probabilities for storms. So here, I think this is actually Hurricane Irene, this red line, and then we've taken this method and sort of divided up the probability space into different tracks and then computed storm surge with that rapid statistical model to come up with 10% chance exceedance. So let's think about 10% chance exceedance. This means that if any one of these events occurs, or excuse me, yeah, I guess if any one of these events occurs, then there's a 10% chance that the water level will get at least this high. And in this high, in this case, is 11 feet is the green. Okay, so what you can see is that there's the risk, if you will, is fairly high over here at 10%. It's not so high on this part of the coast. That's because the hurricanes don't really impact that area when this is the trajectory of the storm. It's also the case that a lot of the ensemble members directly impact this area, where most of the ensemble members that do impact this area are essentially glancing and offshore blows, and that's a quite common situation in North Carolina. I'm unaware that a hurricane has ever made landfall in this area by going from ocean to land. But the other way, I mean land to ocean, happens actually relatively frequently. I mean, certainly Irene and others have done that. So that's kind of one area, another area we're going in. And then finally, this is the last slide. This is my favorite activity, is figuring out how communities can use not only AdCirc, but other models that are out there that are also computing storm surge, and build a community of people that can help inform decision makers sort of at a large scale. This is an example of one of those efforts. This is a MATLAB application that in the lower right-hand side is a collection of AdCirc models that are running, in real time and pumping their data out into this big data grid. And then this application can look at that data grid and then populate its content based solely on the metadata within that data grid. The Hurricane Center actually funded this work in terms of developing this graphical interface to that data, because they can't run AdCirc. They don't have the computer resources, but they're very interested in AdCirc solutions, because AdCirc runs at a significantly higher resolution than anything that they run in-house. And that's not a disparagement in terms of the Hurricane Center. It's just the life that they live in. They don't have the computer resources to run storm surge models at essentially arbitrary resolution. So we've put this together so that they can leverage what the community's doing to potentially help them make, have more information in front of them when they're doing things like storm surge forecasting. So we've actually expanded this significantly in the recent maybe year. And not only is AdCirc in this mix, but the Hurricane Center's own model called SLOSH can be visualized in exactly the same way. And so this actually unifies all these different types of models in sort of one common portal or application, so that, again, they have a lot easier access to the kind of stuff. Now, again, this is complex in terms of the way data gets transferred and managed, and it is a lot of data, but it's not quite big data in the sense of unstructured data or text-based data or streaming data. So anyway, that might be it. Yep, that's it. So this is not a real wave. I think this is a movie. Just wanted to let you know that. But it is the end of the presentation.
Okay.
Thank you.
Thank you so much, Brian. I forgot to say when we started that if you have questions, feel free to type them into the chat window. We can take questions now.
So I'm here in the room with Brian. Brian, you had mentioned the sensitivity of this data given the implications on real estate values and how that sensitivity sort of leads to a great deal of stress of being involved in this kind of process. And I'm wondering if you could talk about the expectations on the team members, whether they're academic researchers or government officials, everyone involved in this entire mapping process. What are the confidentiality expectations or norms or provisions that are in place prior to the final maps being released?
Yeah. Okay. So that's an interesting question. I actually don't know what FEMA requires from the standpoint of confidentiality specifically. When FEMA has a relationship with a consulting firm, which is typically the way these activities get carried out, they have terms and conditions that probably say, you can and can't do this. When universities get involved, there's a little bit of issue regarding, what universities can and can't talk about. However, what tends to happen is because these maps wind up at the community level, and communities then have the right and the privilege of looking at the maps before they become effective and saying, geez, this is a substantial change. And there are substantial changes between maps that were 30 years old and maps that are, you know, much more modern and computed in a much more, I think, scientific way, there's bound to be discrepancies between those two sets of water levels, if you will. And so the issue really is, at what point does this information become public enough to be able to talk about essentially gory details of it and how I mean, and I actually don't know what that distinction is. Our policy, at least internally, is that, you know, we don't answer questions about how the maps get drawn. We don't answer questions of, for the most part, about why the maps are going to say what they're going to say, because there's a lot of money at stake depending on how this ultimately gets sorted out at the community and state and even federal level. So that's not a very satisfactory answer to that question. But the truth is that, you know, until the maps are sort of finalized and out there and being used to set insurance rates, you know, talking at a very high level about the processes is one thing. But we definitely, as an academic group, want to stay away from. I mean, we're not involved in the map making, so we don't really know. And yet we've seen some draft maps that I think our communities have some concerns about specific areas, and so we are working with the state to try to understand the reasons for these relatively higher water levels. But it's inevitable. I mean, if you're going to redo a study with modern techniques and better data, you should expect differences, but that doesn't make communities necessarily feel better about it. So anyway.
Okay, we have another question from Bill Wheaton at RTI, and he's asking, can you say a bit more about how the storm surge, which in your maps always stops at the land's edge, is translated into an estimate of what area will be flooded and to what depth?
Yes. So from the scale at looking at the pictures in this presentation, you may think that it actually stops at land at the boundary between wet and dry, wherever that is. Remember, the wet and dry over the course of a day is changing because the tides are going up and down. So the question of where is mean sea level, let's assume that we can define that. And if you actually zoomed into this picture, which I cannot do here, you would see that a lot of the flooded area actually is on land. So to some fairly good extent, you know, as long as we have the topography data that comes from, you know, this data source called LIDAR to set what the elevations are in an area, then we will get water on land when the storm actually pushes water up that high. It's very hard to see in this picture, but I'm pointing to an area right here which is definitely on land. And I'm going to, this is actually a little bit easier to see here. The black line in this case is mean sea level. So it's the place in our model grid where if you're up, you're land, and you're down, you're in the water. The black line is mean sea level. And so you can see here that there's a lot of area that's flooded. This is water on land. Now the value that you see here, in this case it says 4 meters on land, but that's 4 meters above mean sea level. It doesn't mean that there's 4 meters of water on the ground, because that's a different question. So the answer is that we actually do account for that. This picture shows that is the case. But the last thing I'll say about it is when you get down to here, there's an additional component to that, which is since we don't actually model the process of individual waves sloshing up onto shore, because we have a wave model in ADCIRC, but it's more of a spectral model. It resolves at the frequency level, not at the individual wave level. This part of the process takes our storm surge and wave data and runs it up onto land. And it's actually these elevations or water and wave heights that get put into the map. So there's a step here that we've skipped because we're not involved in that, but that's what I mean. So A, we do model the land and have water level on the land, but there's an additional part which accounts for even higher resolution up onto the land as individual waves ride on top of the storm surge and propagate inland. So.
One more question. can you provide high-level details on data management software, compute environment, and software platforms that you're using?
Yes. So data management, that's the easier one. There isn't anything sophisticated going on here. It's replicated storage, and it's got several different copies of it running around. Again, in terms of sustainability and reproducibility, we need to be able to get to the data to be able to answer questions that come up after the maps are drawn, for example. But also, so the data management is a little bit kind of old school, Unix file systems, cataloging of data, et cetera. The compute environment is, we have a very large set of clusters down in our facility here at RENC. When we computed the North Carolina problem, we had very different hardware, but it was still a very large system that had 4,000 or 5,000 cores on it, and we were running 10 to 12 of these highly parallel simulations at one time. It was an IBM Blue Gene L, if that means anything to that specific question. And so the software, the AdCirc model itself is written in Fortran 90, and that Fortran it may seem old and dinosaur by many perspectives, but it is the language for scientific computing in many respects. All the weather models are in Fortran. All the big ocean models are in Fortran. So it's a Fortran code, runs in a Unix environment. You can run it on a PC, although you may not be able to run it on a very big problem. So that's kind of a quick overview of that question. There's obviously a lot of detail in there that the compilers that get used. Sometimes compilers make quite a big difference in this type of model. Not a gigantic difference, but if you're concerned about 5% over several million CPU hours, then that's something to consider.
Okay, any more questions at this time? Not seeing any. I think that wraps us up for today. Brian, once again, thank you so much, especially doing this at short notice. Thanks to all of you for tuning in. And our next DataBytes monthly webinar will be March 16th. We're moving it back a couple weeks to accommodate our speaker. Our speaker will be Tony Hay, who is the Chief Data Scientist at the United Kingdom Science and Technology Facilities Council, and he's going to discuss the move toward a third age of computing. So look for some details on that coming out in the next few weeks. Once again, thanks, everybody. Have a great Wednesday. Bye-bye.